All right, line A6, learning task 8, which is going to be dealing with three-phase rectifier circuits. And we have dealt with single-phase rectifier circuits before in the past in first year and second year, where we're taking a look at diodes and things like that. Now we're going to start dealing with these on a larger scale on three-phase systems. The very first one that we're going to take a look at is going to be the three-phase half-wave rectifier. But before we do that, we have to go through and just take a quick little refresher on the use of diodes to go and block values of voltage. Because until we're really comfortable with that whole concept, taking a look at the rest of these is going to be confusing at best and, entirely nonsensical at worst. So let's just go take a quick look at a couple of things. First of all, these next couple of illustrations are not in your binder. This is just my own stuff that I've added into here just for sake of explanation. So go ahead and copy them down, draw them, whatever you need to do. But we're just going to go and take a look at DC sources in parallel. Because ultimately we can take any AC supply and we can freeze that AC supply and look at it as a DC voltage at any given point. We change these polarities. That's what we're going to be doing later on. So the first thing we're going to do is we're going to take a look at two batteries that are going to be placed side by side or in parallel. One of these is going to be 10 volts. The other one over here is going to go and be 5 volts. Well, what happens when I go and place two of these side by side? It's really not a lot different than having two separately sized linebackers. I don't really play football. I don't know all of the terms and stuff, who all everybody is, but I do know the terms linebacker and quarterback, and the linebackers are the big guys that are going to be in the front. If I've got a big guy in the front going in this direction, I got a big guy in the front going in this direction, take a look. Both of these have got their positive facing out. They're going to be opposing each other, and what's going to go and happen? Well, everybody knows that the big guy is going to go and overrun the small guy. The small guy's not going to push him over, the big guy's going to overrun him, and the small guy is just going to go and act as if he were a load. We see the same thing anytime that we have got voltage sources that are in parallel and unblocked in between here. We see that my 10 volt supply is going to deliver current along from its negative, and it's going to go and drive it through this supply, backwards through that supply. It should never be going in that direction through supply, and creating a load off of it. The bigger one is always going to go and push through. Well, what would happen if we would go and put parallel sources with diodes inserted? Wow, are we going to go and have anything that's going to happen here? Absolutely, we are going to have something, but we're going to go and have blocking, because we know that a diode has got a positive side and it has got a negative side. As long as the anode, which is going to be the triangle part, is more positive than the cathode, which is going to be the line part, we're going to be able to go and set conduction through these. So if I were to take a look at this one over here, I see that both of these have got a negative attached to them. A negative attached to them over here. So we're going to be able to go and pass that negative through. We can either pass a positive if we would put them up on the top side, or we can pass a negative if we have them down here on the bottom. Both of these are going to go and pass a negative through. This one's going to go and pass the negative from its 10 volts. This is going to go and pass the negative from its 5 volts, or it's going to attempt to pass the negative from the 5 volts, but it won't be able to, because it's going to see this negative 10 volts here, which makes this side at negative 10. And if this is negative 5, in relationship to each other, negative 10 is as if I've got a 10-foot deep pit compared to a negative 5, which is as if I've got a 5-foot deep pit. We see that the negative 5 would be seen as being more positive than what the negative 10 would be down over here. Meaning that this section is going to be more negative, this section is going to be more positive in relationship to each other, which means that this diode over here is going to be blocking. It basically prevents our larger supply from being able to run any current backwards through it. Okay, so we see that the diode goes and blocks any sort of reverse current going through that actual setup over there, which is a big thing that we want to go and prevent, because we don't want to see reverse current through this power supply. We want to protect it because it's the smaller one. We've just got this setup over here, which is going to be that the smaller one is going to be reverse biased and it's going to be blocking. Anytime that I've got voltage sources in parallel, and it doesn't matter how many voltage sources I go and add on in parallel all the way across here, as long as each voltage source has got a diode on it, only the largest voltage sources are going to be able to pass their voltage. Which means that when I go and measure across whatever I have, and once again here we have only got two voltage sources, when I'm going to go and measure across them, I'm only going to go and read my largest voltage that is going to be there. And once again, that's as long as every line has its own diode to go and protect it. So if I were to add in another line over here, we see that we add in another one. Now we've got a 15 volts inside of here. We would then go and take a look at all three of these. We say all three of these, do they each have an individual diode? Yep, that diode is going to go and protect the small ones, and it's only going to pass the largest one. So only the largest one is going to be able to deliver current. And right now we would see that we would get a value of 15 volts that we would go and have for this circuit setup. If I can go and measure voltage across these sources, I can also go and place a load across these sources. If you take a look at this, you see that this load has been placed across. It's in parallel, or it's across all of my sources over here. What voltage is it going to see? Well, it's really no different than the voltmeter. The voltmeter, we just went through that, only sees the largest value because the other two are going to be seen as blocking. The smaller ones are blocking, only the large one is passing, which means that my path for current through here is going to be, let me just try that again. My path for current is going to go and be like that. We're going to go and have a 15 volts plus or minus that we are going to go and drop across here. Really, it's going to be 15 volts minus the 0.7 volt drop that we are going to go and have across this diode over here. So we're going to be sitting about 14.3 volts that we would see over top of this load. You have to grasp this concept that anytime that I've got multiple lines that are all together, every single one of them is going to be protected by a diode, I'm only going to go and pass the largest value. Now let's take this into three-phase theory. Over here, we see something very, very similar. Once again, we see that we have got a three-phase set of windings. We'll identify that over here. These over here, that's going to be three voltage sources. And we know that those voltage sources, each one of them is going to be driven by AC. So they're going to rise to the positive, rise in the negative, back and forth like that, just at differing times, which means each of them are going to peak at differing times. I also see that I've got all three of my individual diodes. I've got a diode per line over here, and that each of those diodes is going to be connected back to a common point where we are going to be able to go and deliver anything through, and from that common point we then have got a common load that is seen across the rest of this that returns back out to that neutral. So it's three main parts. We got our supply, that's the blue, we've got our rectification, that's our yellow, and then we've got our common current path, that's going to be the green path that we are going to see over there. All we need to do is we need to go through our AC sections. And anytime that we go through our AC, we know that we are going to, for a standard phase rotation, we are going to have A, then B, then C, then A, then B, then C, that we are going to have for a standard phase rotation. And all we look for is which one of these at any given instant is going to be more positive. That's what they're doing over here. They're looking at these. First of all, I should just go and point out that the side that we're passing, I'm just going to remove a bunch of these lines over here. We should see that all of these diodes here are only going to go and pass positives. Anytime that this is positive in relationship to the other side, it is going to be able to go and complete a circuit. If I were to follow this through, we'd see that that one could pass, could pass, could pass, could pass, and we could deliver through there. If this is the most positive one in the circuit, if this one would be the most positive one in the circuit, we would see that this one would be able to go and pass through. And if this one were to be the most positive one in the circuit, we would see that this one would be able to go and pass current back through. So we see that there's going to be three loops over here, individual loops, and because we know that AC takes turns, we know that that AC is just going to go and run the yellow loop, then it's going to run the blue loop, then it's going to go and run that green loop that we're going to have. My A phase, my B phase, and my C phase. And it's always going to let whichever with the highest value of voltage take over. Going back to this over here, if this voltage over here, this 15 volts, were going down, and if this 10 volts over here were going up, there would come a point where it would no longer be this that are blocking with this, but if this 15 volts would drop down far enough, this 10 volts would rise far enough, we would go and interchange. And now we would then have this that would go into my conduction, this one over here that would be blocking. That's what happens over here. We can follow this along. We see that right at the very beginning of the graph, we're going to go and see A. That is going to be transferring power. So A is the most positive point in the circuit. You can just draw a vertical line. We'll draw with a green line all the way straight down over here. If we see A, we see that A is a positive. These two are both negative and negative, which means that they would be blocking as far as their diodes would be. This would be a negative, this would be a negative, so they're both going to be blocking. So we see that A is going to be passing. So for the first bit, we are going to go and have A that is going to be passing, but A is still falling away. It's still positive, but it's becoming less and less. Well, at the same time, we see that B is rising. I'm just going to draw another line over there. And if we analyze that line, we would see that B is now the most positive point in the system. This one is positive, but it's just less positive. So we'll stick double positive by the B point there. And this one here is definitely in the negative. Because this is the most positive point in the system, it's the one that would be transferred at that point. And so on, it's going to go. We're just going to go and follow this thing where we are going to go and have hit the max, then it's going to drop down until the next phase picks up and carries over, drops down, picks up, carries over, drops down, picks up, carries over, etc. And so our voltage that's going to be on the output is going to go and be that bumpy line that we are going to see over there. Does that line ever cross through zero? Absolutely not. It does not cross through zero, which means that if we attach any sort of a thyristor onto that line, that thyristor is not going to be able to commutate. It's not going to go and hit that 0 point. So we're going to use these for differing types of applications. Particularly, what we're usually going to do with this is we are going to go and filter this, because right now we're dropping between 0.5 of my maximum value voltage and my actual maximum voltage that I'm going to go and have on here. It's a fairly large pulsation. If we go with a standard 120 volt system, 120 volts, we know that my peak, if I go and divide this by 0.707, it's going to get me to my E peak, or what they call max over here, which would be 170 volts. And then if I'm going to go and drop that to half of my max, that's going to be down to 170 divided by 2, which is going to go and give me 85 volts that I'm going to go and have. So we would have a 85 to 170. And so it's going to be going back and forth, back and forth, back and forth. We would call this value of voltage from here to here is going to be my ripple voltage. V ripple that we are going to go and have. And it's not usually going to be a useful thing to have this ripple voltage. I'm also going to take a look at my ripple frequency. We see that this ripple frequency is going to go and happen lots of times. If I follow a single waveform through, and I'm just going to do that really quickly. If I follow A all the way through here and back up to there, that is going to be where I complete a cycle over there. During that cycle, we see half of a peak, another peak, another peak, another half of a peak. So 2 complete peaks and 2 halves, which gets me to a total of 3. So we're going to go and have a ripple frequency that is going to be 3 times my fundamental. This is not a harmonic. This is just what's called a ripple frequency. So if this was a 60 hertz system, my ripple frequency, F ripple, is going to be 180 hertz. That's going to be 3 times 60 that I'm going to go and have. What we will usually do with these, when we do get these rectified, I'm going to be able to go and take these and I'm going to be able to filter. What I would do is I would take this section over here, I'm just going to erase a bunch of this stuff, and then what I could do is I could go and apply a large inductor in series. Stick that like that. Take a large inductor that is going to be placed in series, and what that inductor would do is that would go and give me a filter, which would then go and allow me to take this frequency here. I'm not going to get to as high of heights, I'm not going to get to as low of the drops over here, but I'm going to go and get a voltage that is going to go and be a little bit offset, but it's going to be smoother voltage. We're not going to have as rapid of rises or as rapid as falls. There's a bunch of different things we could do in filtering, but sticking a very large reactor or choke on there is probably one of the easiest ways for us to go and filter that out. What's our value of DC voltage? Well, our value of DC voltage is going to have to be an average between this peak and between this one over here. And so what I'm going to go and have is I'm going to go and have my DC value that I can go and calculate off of 1.17 times my phase value of voltage. So off of my RMS phase value of voltage, I can go and use this 1.17, which is something that we are going to go and call our form factor. Form factor is just going to go and be a combination of multiple other constants that gets us to what value that we need to go and have for these ones. So for this one over here, if I had 120 volts as my value, I would take that 120 volts, I would multiply it by 1.17, which would get me out to a value of 140 volts. And this would be my DC average value of voltage over here. Last of all, if I take a look at this, each of my diodes is going to go and take turns carrying. We're going to go and have, each of these at one at a time. This one's going to peak, and this one's going to peak, then 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 this one's going to peak. And we see that because all of my phase values are going to go and be the same. We're just taking turns, each splitting up the workload into a third, which means that each of these is going to go and carry a third of the total load current. Now that's going to be an average that I'm going to go and have. In reality, during conduction, this one over here is carrying all, and then it shuts off for this time and for this time over here. So if I average out, total full current going through here, and then no current and no current, divide that by 3, I'm going to go and end up at an average of 1/3 of the value of current, but I do still need to go and size this thing so it's going to be able to go and carry the full current, because when it is conducting, it is the only thing that is going to be conducting inside of that path over there. Okay, that's going to go and cover our half-wave rectifier that we have. Last thing on the half-wave rectifier, because the half-wave rectifier does deliver current back to this point over here, the neutral, it is going to go and be limited to Y type of systems alone. We're never going to be able to go and do half-wave rectification with a delta type of system or anything else. We can only do these things off of Y. It is going to be my simplest one. It requires 3 diodes, or 3 rectifiers that we're going to go and have inside of here. But it is going to give me a fairly high amount of ripple voltage. It says that we use it when the DC output voltage requirements are relatively low. By the voltage requirements, they're talking about the stability of the voltage, how well this thing is going to go and stay stabilized, not about the actual maximum value, because the maximum value is going to be just governed off the size of the system you stick this thing on. And we're also going to use it where the current requirements are moderately large. It's really going to depend upon the size of the rectifiers that we are going to go and use for each one of those. Okay, let's go and talk about our next one, which is going to be the full wave bridge rectifier. This rectifier is best going to be illustrated through the use of me just bouncing an arrow around our 3-phase supply, just to begin with over here before we actually start taking a look at it. Because what we're going to be doing with this 3-phase full wave rectifier is that it has to go and run off of a line-to-line value of voltage. So it really doesn't matter whether we are going to go and use delta or Y. We can use either one of these because this thing is going to be line to line. And so we are going to always be comparing which of my points on my lines is going to be more positive than which of my other points on my lines when I take a look from one line over to the other. If we go back to our previous drawing that we had over here, this is the one that we were using for the single half-wave bridge rectifier over there. What I'm going to do is I'm just going to draw a couple of lines just to show you what line-to-line values of voltage are going to be. And we're always looking for maximum magnitudes of line-to-line values of voltage. Right now, in this point over here, we are going to go and see that my A to C is going to go and give me the maximum value of voltage. If I were to go and look across that whole section over there, the maximum line-to-line value of voltage would be from A to C over there. But then at this next instant over here, we see that the maximum value of voltage would become this B to C value, right? Because the A is dropping down, getting closer towards the C line. So we are going to go and have a maximum value of voltage that is then going to be described across B to C. Then I'm going to go and move to another one again, where now it is going to go from B over to my A. And I'm going to see that the maximum value of line voltage is going to be from B to A. And then when I hit that point over there, we are then going to be, my maximum value is going to be from C to A. C to A, C to A is the biggest span. And then we move over from my C to B, etc. And so what we're going to be doing with this one, this next one, is we are going to be always looking at these maximum spans going from one to the other. A to C right now is that maximum span that we are going to have. Then the next one was going to be my B to C, then it was going to go across from my B to A, etc. as we continue down through here. So we're going to be looking at line-to-line values of voltage. This is just showing the individual phase voltages that are going to be across here, my A, my B, my C. Once we start looking at these things as line-to-line values, we're going to go and see a lot more lines that are going to be inscribed across here. It is going to go and have, my A to C, my B to C, my B to A, my C to A, my C to B, my A to B, my A to C, my B to C, etc. We're going to go and have all of these rotations that we are taking through here where we're going AC, then BC. And if I take that down into this over here, my AC and BC, I'm going to go and have A to C, and then I'm going to go and have my B to C, which would mean that it would be the same as if I were to take this. Let me see, I don't know if I can drag. It's not really dragging it the way that I want it. Okay, well, I'll just rotate it then. Then I would go over to my B to C. And then from my B to C, we would keep that point anchored, and then we would go and rotate this thing, and it would go B to A. And then I would go and keep that point anchored, and it would rotate then over to the A side over here, etc. It's kind of poor visualization right now on the keyboard like this, so I'm just going to go and grab that one off there. It's really a lot easier for us to go and do these type of things whenever I have got an actual live classroom and a stick that I can go over top, because we can really see how the flux moves from one point to another point. And if you go back to the very beginning of your three-phase theory, you'll see that very first set of transformers where they were showing you the transformer flux, component to component to component, we saw that there would always be one of those lines that would go and stay the same, or one of those lines of flux that was going to go and stay the same inside, and it just gives us this rotating value of voltage that's going around from component to component. Ultimately, what it's doing for us inside of here is we are always going to be looking for our largest span of voltage, because whenever one of these is going to be seen as being very, very high, let's say that the A is going to be seen as being very, very high, I would then be able to go and say at the same time my A is really, really high, I'm going to go and see across to here that my C is going to be really, really low. And so my highest high is going to be an A, my lowest low is going to be a C right now, which means that my path for current is going to go across the maximum. So if this is my supply, it's going to ignore this B because it's not at a peak right now. My C is going to be able to pass a negative. So I'm going to take that through. I'm going to look for which side can pass a negative, D3 or D6. D3 is going to be blocking because it's going to have the anode, therefore it must be D6. D6 passes the negative through to here. That current can go through to there. I'm going to follow back from the other side right now from my A where it's positive. I take that in here, and we see that D1 is going to go and be positive. D4 is going to be reverse biased because we've got a positive attached to my cathode. So D1 would be the only one that would be passing current at this point. So we see that right now we're going to go and have two of these that are going to go and be passing. The other ones are all going to go and be blocking because my value of B at this point is going to be insufficient for it to be the greatest amount on anything, which means that these over here, oops, sorry, that's my B's. These over here are going to be blocking because it's not large of magnitude. These two, D3 and D4, are going to be blocking because it's the wrong polarity that we have off of them. So we would go and have our A to C that is then first going to go and start. Then the next thing that's going to change is that my positive peak is going to then move over to my B. So we'll move the positive peak over to the B, which would mean that I'm going to go and lose the top part of this, lose that top part. Still going to go and maintain the bottom part of that. This is now going to go and become my most positive point. And when this becomes my most positive point, now I'm going to be able to go and assess these ones. One of these is going to be forward biased. That's going to be D2. It's going to go and have a positive applied to its anode. We're going to be able to pass it all the way through to there. This one over here is going to be reverse biased, so it's going to be blocking. This one's going to stay reverse biased. And these two over here are both going to be reverse biased and blocking because the magnitude of voltage is going to be insufficient to go and cause any sort of triggering. We would then be able to follow on to the next one. I hope you're following along on figure 4. The next one would be my B to A. So we just moved that one down there. So now we would move this one up here. That would be my next move, which would be taking this one to a negative over here. So we'll just erase a bunch of these. Those ones are going to go and be gone over there. If this is going to become my most negative point, we can then go and take that, erase a bunch of these here right now. We can then go and take that negative from here, pass it into here. We say, well, which one's it going to pass? It's going to pass through my D4, which means that we are going to once again have a complete path for current flow through here. It's going to be a line-to-line value of voltage. And this would work whether we were using a delta or whether we were using a Y as our source. In some ways, it's actually easier to go and see it, off of a delta source than it is off of a Y, because you've just got that triangle. That's going to be, two of these are conducting, one of them's kind of in the middle and not doing anything at any given time. What does it give us for an overall value of voltage? Well, it's going to give us a much better value of voltage than the half-wave rectifier. I mean, we should be pretty used to this at this point, that full-wave rectifiers are better than half-wave rectifiers. We're going to go and get larger values of DC that we're going to get out of the same supply voltage. Instead of us having, if we have a 208 from line to line, we're going to be sitting pretty close to that 208 line to line because we're so rapidly changing over from phase to phase to phase. Going back to this drawing over here, we see that we are only going to be from 90 to 150. That's a total of 60 degrees. And then we kick over. Then we run from 150 all the way over here to 210, and then we kick over. It's always going to be 60 degrees, 60 degrees, 60 degrees, 60 degrees that we're going to go and kick over from one to the next, which means that if I'm kicking over every 60 degrees of a 360 degree rotation, that's going to be a complete sine wave over there. That means that I'm going to go and kick over 6 times, right? 360 divided by 60 means that I kick over 60, 60, 60, 60, 60, 60 over there. This is one complete sine wave. We'll trace this one over here because it's an easy one to see. During one complete sine wave, I go through 6 mini pulses over here on the top with this full wave bridge rectifier. Those little mini pulses are going to go and have much smaller drops than what we had on the half-wave bridge rectifier. Instead of us dropping down ridiculously low, we're only going to drop down to this value, 0.866 of our line voltage max. You've seen this number, 0.866. We've dealt with this one before. It's a 3-phase developed multiplier. We saw this one when we were working with our open delta transformer supplies. Open delta transformer supplies, how many windings? 2 windings. How many windings are active at any given time inside of here? 2 windings. There's a whole mathematical relationship between all of that, but I'm not going to go and worry too much about that. We're just going to go and say that, look, this is a 0.866 of my maximum line is what I'm going to be dropping down to because I've only got 2 windings active. I'm going to go between that 0.866 of my peak all the way over to my actual peak. So I'm going back and forth between those 2 voltage values of voltage, which means that my average between those 2 is going to have to sit somewhere in between. The average for these is going to be found by using a form factor of 1.35 that we are going to go and have over here. If we were to go and use this one that we had over here, it was a 122.08 volt system. Just erase a whole pile of stuff here. If I've got this 122.08 volt system here, we're going to go and use 208 as our line value voltage that we will use for our analysis. So over here, what we're going to see for our maximum, or for our DC, is going to be 1.35 times my line value. Note that the line value here is an RMS value of voltage that we're dealing with. It's very critical that you understand that these little multipliers, the form factors, always work off of your RMS, or the value that we mostly go and work with. Take that 208, multiply it by, this 1.35, and when you go and do so, you're going to come out to a value of 281. That's going to be this line over here, 281 volts DC that we're going to have. It's going to be a bumpy DC, but it is all DC. It never changes direction. If we wanted to know what our peak was, we would just have to go and use our standard peak formulas. That's going to be my ERMS times 1.414, or ERMS divided by 0.707. Either one of those is going to go and get you to your peak value, which in this case, you take 208 multiplied by 1.414, it gets you to 294. So that would be my peak. 294. And if I want to find the absolute bottom of my value over here, I would have to go and take this times 0.866 of my maximum. So if I have got my maximum value, that's going to go and be 294. I'm going to take 294 times 0.866, which is going to go and get me to 255. Note that in your book they give this as sine 60. The sine 60 is just to do with instantaneous values of voltage. Instantaneous is going to be my Emax times my sine. It's just telling me that, look, we're picking this thing up right over there at 60 degrees in and 60 degrees in, etc. So my bottom line over here is going to be 255. What is my ripple value of voltage? My ripple value of voltage is the difference between this voltage and this voltage. So 255 to 295 is going to be a value of 39 volts ripple. The ripple (39 volts) that we are going to go and have. My ripple frequency is going to be 6 times my fundamental. So if I have got a 60 hertz system, I see that I get 6 mini bumps that we are going to go and complete inside of one complete cycle. We traced that through before, right? Here's a complete cycle, which means that I'm going to go and have 60 hertz times 6, which is going to go and get me up to 360 hertz that I'm going to go and have. Last of all, if I'm going to go and take a look at my diodes, and I forgot to do this on the other one, my diodes, when they are not operational, so anytime that I'm blocking anything, they are going to go and have to block the peak of whatever my system line voltage is going to be. In this case, my system line voltage is 208. My peak of that, I take 208 divided by 0.707, which gets me up to this value of 294. So I'm going to need to be blocking at least 294. In reality, you're probably going to go, 1.5 or 2 times greater than that, because there's not a huge value of cost differential going up like that from one to the other. But you do want to go and make sure that you're going to go and protect those diodes. Same with the other one here, actually, and I forgot to go and do this one before. Oh, sorry. This one over here. Nope. This one over here. That's the one we're looking for. The half-wave rectifier for my blocking. Anytime that I'm going to be blocking, I'm going to go and be blocking line-to-line value of voltage, with whichever of these that are going to be blocking. Take a look at this for a second. Okay, well, let's just say that right now the most positive one inside of here is A. If A is the most positive, that would mean that my path for current right now would be through here and through here, which would mean that these two over here would be blocking. Well, A is going to go and be most positive. If I take a look at this mini loop over here, that is a line-to-line loop that I'm going to go and see. This one over here, the top one, is conducting, which means it's acting as if it were a closed switch, which means we're pressing the full line-to-line across that diode from here to here. And it would be the exact same for the other diode as well. Once again, anytime that we're building these rectifiers, line-to-line value of voltage, find what that is. That is going to go and be the peak of that. That is going to be your absolute maximum that you are going to need to be able to go and block. The very last thing that we can do is, instead of using just a standard diode over here, we can go and take these diodes and we can get those specialized controllable diodes that you're all familiar with, which are going to be called a SCR, silicon control rectifier, which does 2 things. It controls and it rectifies. Remember, it's got that third leg off of it, the gate, where we can go and say, here's where my waveform is, and I can choose to turn it on right here and then carry the rest of this section through. Or I can wait till later on inside of there, and I can only carry this section through, etc. And then it cuts off the whole other section, the lower section. So each of these just acts as a rectifier and a controller. What I'm able to do then is I'm able to go and take a look at what would be my maximum value of voltage that I could go and get out of this system. And then once I know what that value of voltage is, I can just say I can cut away anything smaller than that. Here's how we would go and do that over here. In this case, we got 460 volts that we are going to go and have. That 460 volts, we would just go and say, if this is 460 volts, is this, first of all, going to be a full wave rectified circuit? Yes, it certainly is. We see the 6 SCRs on there. So let's go and take 460 times 1.35. That's our form factor, 460 times 1.35, which is going to go and get me to my DC value of voltage. 460 times 1.35 Gets me out to a DC value of 621. We know that in reality, it's going a little bit higher on the peaks and it's going a little bit lower on the drops, but we know that this 621 is what we're going to be seeing up here. So 621 would be my DC, I just wrote over the top of that there, would be my DC maximum that I would go and have, and by me then going and taking those peaks and just trimming away, cutting away, putting less and less of it through at a time, I'm going to be able to go all the way from 621 volts. I'm going to be able to cut away more and more and more until eventually I'm down to that I've cut it all away and I'm left with 0 volts. It's great for controlling my loads. If I've got a DC load over here, and this is not a variable frequency drive that we're talking about, this is just a DC control where I can now go between 0 to 621 volts DC by chopping it away. It's going to be a nasty, ugly looking waveform. Lots of drops and peaks and stuff like that. We would want to go and filter it, but it would allow us to go and get variable values of DC out. We're going to look at that stuff later on once we get into motor controllers and drives and soft starts and stuff like that, how we actually use those values of DC to go and change, what we're going to be outputting onto stuff. All right, that's this one.